Hello, Physics 20s. This is lesson 6.1 on kinetic and potential energy. So first thing, potential energy and kinetic energy. The concept of energy is just that ability to do work, meaning kinetic energy is essentially just energy stored in motion, right? Energy stored in motion. The idea of storing energy within the motion means that the motion of an object can cause a force through a distance on something, right? Because of the motion within the system. And so, for example, if you've got a ball, a very heavy medicine ball coming towards you, you might really feel that force and be impacted by some sort of distance because of the motion of that ball as it comes into contact with you. Potential energy is just energy stored, okay, in the position within a field. Position in a field. Right? So let's take again a look at that same big medicine ball. It can have some sort of impact on you. It's not moving, but because of its location, because it is there, that can cause some serious force through some sort of distance upon you just by there. Now it is the potential to do work. It's stored in there. It is not actually applying the force until it happens. Now the reference point in terms of potential energy, because it's due to position. Well, position of what? Right? This reference point is key for potential energy because it is basically saying from what point are you measuring the field? Are you right? And so, for example, if we've got this big rock here, but this person is standing here and another person is standing here, big rocks are within the same, essentially, position within the field, gravitational field of Earth, but the amount of potential here compared to here, or the amount of potential energy that is stored within these two big medicine balls is going to be different. So kinetic energy is essentially just 1/2 mv squared. That is the formula that we're going to be using for that. And for potential energy, we're going to use mgh. These are basically force, ma, times distance. A little bit happening here within there, but we're just going to go with it. Now, one thing, because energy is just the ability to do work, we can say that the change in energy is essentially the amount of work done to an object. And we'll take a look at a few examples here in a little bit. So, let's take a look at example number 1. We've got an object. It is sitting 2.5 meters above the floor. It is 15.0 kilograms. We're asked to find the gravitational potential energy. So mgh, that mass of 15, g is 9.81, and the height being 2.5 meters means that the potential energy there is going to be 368 joules. Unit for energy is joules, same as work, because really energy is just the ability to do work. Mentioned that ability to do work. Now, in the case of the bow and arrow, if we've got a bow that is put here, and then some sort of force is going to act upon it. So we have a force that's going to bring it back to this point here, right, as the arrow sinks in. The amount of energy stored within the system is really the amount of work that's being done, which means force times the distance. Now we are pulling this back with 120 newtons of force, 0.606 meters, which means the amount of energy stored here is 72.7 joules. Okay, let's take a look at our third example here. Now, in this case, we've got a student who is running uniform speed, and so the energy being stored here is due to the motion of the student, not due to the student's position. And so we're going to use the 1/2 mv squared, and you're going to find here that the kinetic energy is 219 joules. That's just plug and chug 1/2 times 60 times 2.7. Make sure you've got the squared. Of course, these equations can be manipulated. In this case, we're looking for the velocity of the object given the mass and the kinetic energy, 135 joules. So you'll multiply both sides by 2, divide both sides by mass, and square root in order to get the velocity. So 2 times 135 divided by 2.1, all square rooted, gets you the velocity, or the velocity of 11.3 meters per second. So just taking a look at what we mean by reference point again, here we've got a pendulum. Now this pendulum is not touching the earth, but really, as we take a look about the potential energy, it's all going to swing down. This is as low as this ball is going to go, assuming the string doesn't snap. And so this here is 25 centimeters above this equilibrium position. Now this is a 75 centimeter string, and again the string is just moving this way, which means that this distance here would be 50 centimeters. So the potential we're really doing is we're comparing it to here. This is our reference position. And so EP is equal to mgh. That potential energy is 0.25 kilos, 9.81 meters per second squared, and 0.25 meters above the height, which means that this potential energy is 0.613 joules. Now example number 6 says, well, what if that's all converted, bad word there, it uses a mechanical force to mechanical pathway to now be stored as motion here at the bottom. And so really this is similar to number 4, where we're going to just take 1/2 mv squared, or 2e over m all square rooted is equal to v. This is all for number 5. And your velocity there should wind up being 2.2 meters per second. You should be, again, going through these numbers, taking a look as you're kind of going through. One more question. What angle? And this is kind of just taking a look at what we've got going on. Now, if this was 75, this was 50, as we already discussed, because we had this additional 25. Really, we're just looking for what that angle is. Well, the 50 centimeters is on the adjacent side, this is on the hypotenuse side, making a 90-degree angle there. So cosine theta is equal to adjacent over hypotenuse. That adjacent side is 50, the hypotenuse being 75. So 0.6 repeating, and you're going to inverse cos to both sides in order to find the angle, which will be, in this case, 48 degrees. Make sure you calculate this in degrees when you got questions like that. It doesn't happen a lot, but I thought I'd mention it just kind of as one of those things. Again, if you got any questions, let me know.